Math 13 students, welcome. Here's an introduction to the notion of inferential statistics. This is module 3. So let's go ahead and take a look at what inferential statistics is all about. I'll introduce some basic theory, and I don't think there's really any math involved, and we have some basic examples. All right, module 3, inferential statistics. An introduction to the notion of inferential statistics. So, in this presentation, we're going to introduce this notion. We're going to identify a need for the central limit theorem, and we'll introduce appropriate examples as we go through this basic introduction. I'll start with a definition of inference. Inference, it's a noun. And it's a conclusion that is reached on the basis of evidence and reasoning. It's not a random guess. It has its basis in fact and logic. There is a need for inferential statistics. Populations are large. The parameters such as the mean and the standard deviation, things like that, are truly unknowable. Now, sometimes we really do need to know those values because we'll need to make decisions that are rooted in those values. So what do we do? Samples are small by comparison. However, we know everything there is possible to know about our sample. We know the mean, the standard deviation, the sample size, how it was collected. We know an awful lot about our sample. Can a sample provide a reasonable estimate of a population parameter, such as a mean or a standard deviation? Can I reasonably extrapolate from that sample to the larger unknowable population? This is where probability comes into play because it is essentially kind of a guess. It's an educated guess, but it's really a guess. There is a real need for this notion of estimation. Consider the case of a pandemic. There's maybe a vaccine being developed. Not everyone's going to take that vaccine for any number of reasons. So we need a way to do two distinctly different things. We need to estimate the effect of the population at large. Can it protect enough people? And we need to estimate the percentage of the population who will actually take the vaccine. How many doses are going to be required? How do we reach populations that might be difficult to reach? These are the types of questions that need to be answered. They can't be answered explicitly or exactly because populations are just too big. However, we can make estimates and test claims. This is where the central limit theorem comes into play. We count on that central limit theorem to provide sample statistics that don't differ too much from population parameters. We'll have a sample. Some of them might be far from the true population mean. Some of the samples might be close to the true population mean. I'll have one of those, I just don't know which one. The probability, though, that I have a sample that is far from the true population parameter is relatively small. The probability that I get a sample that is closer to the true mean or other parameter is actually much better. Here's the issue. I have just a single sample, and I really count on the central limit theorem to give me a high probability of getting a sample that is close and a low probability of getting one that is far from the true mean. Now, the central limit theorem claims that as n increases, the sample statistic will better approximate that underlying parameter. So x bar will pack more tightly about the true population mean mu as n increases. So x bar is likely to be close to the true population mean mu. And this works for other parameters too. I like to start in this discussion with the mean because we've had a lot of experience with that, but it works for other parameters as well. Now, when n does become large and those sample statistics do pack close to the parameter, we like to turn this around. We don't know where that parameter is. All we have is my sample, but I know the parameter is probably close. That probability is high, as long as my sample size is large enough. And now, there's a couple of distinctly different uses of inferential statistics that we encounter this semester. We use this in two ways. First, we use it for estimation. We use a sample mean to estimate a population parameter, maybe x bar to estimate mu, maybe p hat to estimate p. The other use is in the notion of a test of hypothesis. We can test a claim about a population parameter, and we can determine how likely the claim is to be true. For example, we may test the claim that 60% of students pass an online class this semester, and then collect a sample to test this claim. So these are two distinctly different yet related tasks that we deal with this semester. So we've introduced this notion of inferential statistics. We've identified a need for the central limit theorem, and we've taken a look at some very, very simple examples to help us get a handle on what this might look like. We're going to start with estimating a population proportion using p hat. That's the first part of chapter 7. I'll have more videos on that, and you can find them down below here in the rest of the technical detail for chapter 7. That brings me to the end of this presentation. I'll say goodbye, look for more videos, and do your homework and come talk to me. Thank you.